All right, greetings everyone. Welcome to the third part of the video now for section 6.1. And now that we have some ideas of the basics of what a sine and cosine function look like, we're going to start to get into transformations of those functions. So what I'm going to do first here is draw a basic sine wave, and I'm going to draw it on a little different scale than I did before. So this time I'm going to call this one this negative one, meaning that this is where 2 is, and this is where negative 2 is. And then we saw that with those, the basic shape of a sine function or a sine wave looked something like this. So here in green, I'm going to call that function f of x equals sine of x. And we're going to look at what happens if we do some transformations here. So the first thing I want to look at, or first example, is a function that I'm going to call g of x, which is going to be given by 2 times sine of x. And if it's 2 times sine of x, it really means, since over here we have that sine of x is f of x, we're really saying 2 times f of x. And so we have to think about, back to PreCalc 1 or whichever course you took before this, what does putting this 2 here on the outside of the function do to the function? And the answer, if you recall, is that it causes a vertical stretch, which means all of the output values at these different points get doubled. So we can go through for each point. So, whoops, not that. Go through for each of these points here and double their output values. So at negative 2 pi, we double the 0, it makes 0. At negative 3 pi over 2, double the 1, and that makes 2. At negative pi, double the 0, it makes 0. Negative pi over 2, double the 0, it makes negative 2. At 0, double that, we're back at 0. At pi over 2, double 1, we have 2. At pi, we see that stays at 0. At 3 pi over 2, it goes down to negative 1, negative 2, excuse me, and then at 2 pi, we get that. So our transformed function would look something like this with the vertical stretch. Now, also notice what that's done. If I draw in the midline here, notice that that vertical stretch there tells us how far above or below the midline the function is going, right? So notice for having a 2 there, we see that in each of these cases where these peaks and valleys are, the function is either going 2 units above or 2 units below it. Okay, so that is interesting. Let's look now what would happen if we had a function, and I'm going to call this one h of x, where the formula for h of x was sine of x plus 1. So I'm just going to add a 1 there on the end. Well, what does that do? Well, we again think back to PreCalc 1, stuff we learned there. And you may recall that that plus 1 there shifts everything vertically up a unit. So every point we have here is going to go up 1 unit. So this 2 pi 0 would go up to 2 pi 1. Negative 3 pi over 2, 1 would go up to negative 3 pi over 2, 2. And we could do that with all of the other points. Okay, and we see that what we get then is this function I am drawing in red here. Okay, and let me highlight that a little bit more to make it stand out. So this thing here that is traced in red, that would be our new function. And notice, in addition to moving everything up 1 unit, that shift of plus 1 also changed the midline. right? For the original green function, it was that red line, horizontal line. Now it's going to be this orange horizontal line here. All right. Okay. So we can formalize this stuff a little bit more with some terminology. And so, as I kind of already been using, the midline of a function, or of a sinusoidal function, that's the value that it oscillates above and below. And it also corresponds to the vertical shift. And so because of that, if we have a function like, say, f of theta equals cosine of theta plus k, or this will also work if it's sine of theta plus k, well, the midline then will be a horizontal line at y equals k, or whatever our output variable is equals k. All right. And then we also have a special name for that distance that the function oscillates above and below the midline. So here in this picture that I have down below here, notice there's my midline, and they have labeled that distance that the function is going above or below that midline as the amplitude. Okay. And you can also see here kind of a way to find the amplitude of a function. So here, notice that for this one, the max value of the function is 1, the min value is -1. And so to find the amplitude down here, they did 1/2 times max minus min, and that gave them the amplitude. So one way, if you have a graph and you're trying to figure out the amplitude, one way you can do that is, again, doing 1/2 times the max value minus the min. Okay. All right. Let's also now do some graphing. And I'm going to use Desmos for this graph. However, you could also do this on your graphing calculator if you have one. As I've mentioned earlier in this chapter or this section, to graph these functions, make sure that your calculator is in radians mode. So I'm going to go ahead and switch to this window. And so notice here I've got things more or less set up like we had in the PowerPoint. So you see a min value of -1, max value of 1, and then I'm counting along the horizontal axis here by pi over 2. And what we're going to do is we're going to graph two functions. So we're going to start by graphing f of x equals sine of x. So there's our sine wave. And then before I graph it, we're going to graph a function that I'm going to call g of x. That is equal to sine of 2x. So notice we've put this 2 here on the inside of the function. And before we graph it, I just want us to predict how will this change the graph of the function f. Having that 2 on the inside. We again have to think about our knowledge from PreCalc 1. If we make a change on the inside of the function, that impacts the inputs, which means it causes horizontal changes. Also, we know that the inside of the function is sometimes called the house of lies, so it does the opposite of what we think. So even though there's a 2 on the inside, which would make us think it's going to stretch things, that means it's probably going to compress things. So it makes us guess then that having the 2 on the inside will do a horizontal compression for this function. So let's check our hypothesis now. So I'm going to call this g of x equals sine. And I'm going to do 2x. And notice, yes, we have gotten a horizontal compression, right? It's taken that function there in red, so this one here, and it's squeezed down a period of that to be half of what it was before, right? So notice now one period, rather than going between 0 and 2 pi, goes between just 0 and pi. So we have in fact seen a horizontal compression there. And again, as I just kind of mentioned, the period has been changed. All right, so let's go back to the PowerPoint slides, and we'll just kind of put all of this together. So this gives us these different things I've talked about in the last few minutes give us kind of some general formulas for sine and cosine functions. So we can have f of t or f of x or whatever our variable is equals a times sine of bt plus k, or have a similar thing for cosine. And in this function, that value a will always be our vertical stretch, and that gives us the amplitude. So that distance we go above and below the midline, which you see there in the picture. The value b gives us the horizontal stretch compression and is related to the period, and the period will be equal to 2 pi over that value for b. Now be very careful. Notice this does not say that the value for b is the period. It can just help us find the period, again, by doing 2 pi divided by that value. And then the value k there, that tells us where the midline is. So as you can see again in the picture, the value of k tells us where to draw our midline here. Okay? All right, that's it for now. Thank you for watching.